Before moving on to the new problems that we'll be taking up today, let's quickly look into what we have discussed before. So we have talked about states of the form dp of I comma some extra constraint like weight in case of knapsack or count in case of some constraint given that how many items you need to take of the first I element. These kind of constraint type knapsack styled states are common. This we have already discussed. Apart from that, we talked about dp of some state which is going to be game. Okay, that how do we decide on whether it's a winning or losing state in a game. Okay, in fact this was the last thing that we discussed. Apart from that, we have also talked about some dp of I which is ending at I and extending the idea, like extending the solutions after that. Okay, we have talked about dp of something like L2R. So we talked about one particular problem in the Saturday session where you have a whole array and you can take the first element or the last element in the array and you have to decide on what is the optimal game in which you can play. So in that we took this particular kind of state and this basically gave us the optimal play, some sort of optimal for range L2R, right? So these are the four types of state that we have looked into. Okay, so we will talk about few more problems so that we can look into how we can use these states more efficiently. Now, of course, as soon as we get into these few classical problems that we have talked till now, that does not ensure that you already know about all these states yet. It basically means that you now know that something like this exists and I can apply one of these type of states to a particular problem. Okay, so now in your mind you should have some sort of checklist kind of thing that okay, when you see that okay, I'm thinking okay, this problem can be a dp problem or I need to form some sort of recursion. So can I create a recursion of this form, can I create a recursion of this form, can I create a recursion of this form, and so on, right? So this is the basic pattern that you need to recognize from these things, that okay, these are the kinds of recurrences that are occurring up frequently and we need to think in terms of these states. Okay, one more state that we have talked about in the LCS1, that is like for strings mostly, that optimal for s of 0 to I and s1 of 0 to I, s2 of 0 to j. Make sense? So this kind of for string kind of problems, this kind of states are more predominant, and that's why this is there. Okay, so these five kind of states are mostly there that you definitely need to know. Okay, so whenever you are thinking for a problem and thinking about okay, this can be a dp, what can I take for the states, this is the list that you should keep in mind. Okay, I need to think about, can I go about taking something like this? Okay, of course there might be more states, like of course these things can have extra things that are not written over here, right? So we can keep on more parameters to maintain some property or to count uniquely or count distincts and something like that, but these are the basic iteration styles in which we are doing, right? So the idea is more or less this. So today we'll be talking about few problems and we'll be looking at what kind of dp states work for them. Okay. So let me start with the first problem then. So in this particular problem, let's say you are given an array of size n. Okay. Now in this particular array, what kind of operation that you can, there is an operation which you can do on this array, in which what you can do is you can take any two elements that are neighboring, okay, like some I, a of I and a of I plus 1. Okay. You can merge them into a new element which is going to be equal to a of I plus a of I plus 1 mod 100. Okay, so after merging these two elements, the new element will have the value a of I plus a of I plus 1 mod 100. Okay, and this particular merging will give you some reward, let's say, of which is of value ai times ai plus 1. So this is going to be the reward for this particular step, like to merge it in this fashion. Make sense? Now we need to find out how do we merge all the elements in the array to one particular element. So let's say there is initially 1, 3, 4. Okay, so let's say we merge these two elements, so we will get a new element 7 after 1. Okay, let's take one more element 5 over here. Okay, so if we merge these two, so we will get a reward of 3 into 4, 12. Okay, and the new array will become this, right? So this is what we are doing, that we are merging two elements that are neighboring in the array, and from that we are getting these sort of elements, right? Now from this particular array, like then again we will do some sort of operation like this in this particular array, and we will get, let's say, 8 over here, and the reward would be 7, and then there is 5. We merge these, and then we get 8 plus 5, 13. Mod 100 is not going to help in this particular case because it's a pretty large number, but in general the numbers can become large and they can like go beyond 100, and then it will become mod 100. Then this particular value will give me a reward of 8 5s of 40, and my total reward would be 12 plus 7 plus 40, right? So my total reward in this process is defined as each of the steps reward. Okay, so I need to maximize my total reward. So find out how can what is the maximum possible total reward that you can create. Okay, so just as a quick recap, you have an operation in which in this array you can merge any two neighboring elements. So on merging, you get their product as your like reward, and the new element after merging will be of value ai plus 1 mod 100. Okay, and this is kind of like one example. Okay, you need to find out what is the like in what order or in what fashion in which you will do this particular operation such that the total reward that you get at the end is maximum possible. Okay, is the question clear to everyone? Can I have +1 if this is clear to everyone, or if you have any clarifications you can ask. Okay. So let me give you constraints as well real quick. So n is going to be equal up to 500, and ai is going to be equal to 100. Okay, less than 100, because anyways we are going to like everything will remain always less than 100, right? Even after merging, because this operation is holding true. So you need to find what is the maximum profit that you can create. Think about this problem for a minute. So we have this sort of list that you have in your mind that okay, these can be the states. How do we apply in this particular problem? Any ideas on which kind of state should we keep in this particular problem? So of course, the main part that you need to think about is states, because once you get like, of course, when you are thinking about state, you need to think about transitions as well, because will that state work depends on can you design a transition or not. So it's like more or less coupled. So if you think about a state, that's like once you are done with state and transition, you're done with the problem, right? Because then it's just implementing that with proper base cases and everything. So first of all, the main like crux of DP what people struggle with is generally the finding the correct state for the problem. So what can we use in this particular problem? What state can we use over here? dp of L are merged value. Okay. That dp of L R merged value will give me what is the optimal way to merge L to R into a given merged value. Is that what you're thinking? So this will some sort of work, but we can do better than this. Like this is not the most optimal way for this time. So more or less the idea is correct that it's dp of L R some sort of merge. Like what is the optimal way to merge some subpart L to R. Okay. Now in that particular state you are keeping merged values, but do we need to keep merged values in this particular problem? So do we need merged value? It turns out we don't need to keep the merged value into the recursion. So just keeping dp of LR, that what is the most optimal way to merge this whole range, okay, into one element. Okay, what is the most optimal way? Like there are r minus L plus one number of elements, so you will need r minus L number of merging to get to a final element, right? So what is the most optimal way, like minimum, what is the maximum cost, maximum reward that you can create in merging all of these, right? So how do we calculate that out? So it turns out it is, this is what this thing is. Okay, so this would be max reward to merge segment L to R. Okay, so basically what is going to happen in this, so this is how we try to think of transitions, that when you're thinking about this particular state, how will you know that this will work or not? Okay, so one of the ways in which these kind of states work is, so this particular whole range will, so let's say there is a finally one element, right? There is a some element that is of value x that is going to be there in the, once you reduce this whole L to R, okay, some value x. Make sense? Now if we think about it from the end, there must have been two values at the end, and they must have got merged and gave us this one value, right, with some reward. Make sense? Is everyone clear with this, that this can only occur like in the, like last but one move, there were two elements, okay, and both of them merged to give me the one value. Is this clear to everyone, that this is what is going to happen at the end in this state? Okay, so there was some value x at the end. When we merge these two in the last step, they get to this value x. Okay, that this is something happening. Now I don't know what this is. Let's say this is y and this is z. Okay, some values z. Okay. Now observation number one, that when we are merging these two values, this y corresponds to some segment like this in the array, okay, and this z corresponds to some segment like this in the array. Okay, like y will come by merging some segment like this, z will come by merging something like this, and then they will get merged to get to this value, right? Now why is this happening? Note that we are always merging neighboring two elements, right? So a element over here can never get merged with something like this and then like they go to one side. it's always like some continuous range from L to some mid, let's say, let's call this element mid, okay, and then mid plus 1 to R, okay. There are two ranges that will get merged into two elements and then they will finally get merged. Is this making sense to everyone? Can I have a plus one if this is clear? That there would be two continuous range broken by, let's say, some mid, some hypothetical value mid, in which like the elements from L to mid will get merged into one element because like they are neighboring merge, right? So only this neighbor did not get merged any time anywhere in the whole sequence. So maybe two elements got merged over here and here. Then these two got merged. Then something like these got merged, and so on. A lot of merging happened, and then you got to some y. And over here as well, this never happened. That there is nothing, no cross merge across this boundary, and things over here merged, and they got to this set, right? So this is first observation that for the, like, let's say this is nth step, so n minus 1th step, that the two elements come from two different ranges, right? So this give us a idea that okay, I can calculate some sort of like resulting value, like some sort of value from by breaking this L to R into L to mid and mid plus 1 to R. That what is the optimal way to decompose these two ranges into two values, okay? Let's look at one more kind of observation in this particular problem, okay? We were having an expression that when we were merging two elements, a1, a2, okay, the value was a1 plus a2 mod 100, right? uh, Edge elements, can about edge elements, okay. So let's say there are, let's say, four elements, okay, a1, a2, a3, a4, okay. So there are, so let's say there is finally one element, right? So for the previous two elements there can be possibility that okay, a1 remains like that and these all got merged and then they are going to get merged, okay. The next possibility is a1 a2 got merged into this element, and a2 a3 a4 got merged into this element and then they got merged, right? This is one possibility. The next one is a1 a2 a3 got merged together, a4 got merged, a4 did not do anything, so these got to two elements and then they got merged to get one element, right? So these are the different possibilities. So that's the only ways that can happen, right? Is this clear? That this is the only n minus 1th step possibilities that can happen, okay. No, mid is some point mid in the range. It's not exact mid. It's just it's something that we will iterate on. It's not fixed, okay. We will have to try all possible mids, some sort of, okay, all possible mids in the range L2R, okay. Now let's look into this particular expression that we have, that a1 a2 got merged into a1 plus a2 mod 100, okay. Now let's say this got merged with another value a3. What would be the final value? Can I write that to be equal to a1 plus a2 plus a3 mod 100? Because note that this expression holds true, that a1 plus a2 mod x, I'm going to write it in this fashion, a1 mod x plus a2 whole mod x is equal to a1 plus a2 whole mod x, right? Is this making sense? Because anyways this holds true, right? Because if you take finally one mod, anything that you had to take mod in between also got mod by that mod, right? Like module operation works in this fashion, right? Is this clear? Is this clear to everyone? That now this basically leads to one nice observation, that if in the array we had to merge, like let's say from some L2, like let's say we had to merge a1 a2, let's say al plus 1, so on up to ar, okay. If we had to merge all these elements into a final value, can can you think of what would be the final value of the element? if we have to merge, let's say al plus 1, al plus 2, like these are the array elements up to r, and we have to merge all of them into one value. Okay, what is this final value going to be? Prefix of r minus prefix of l? That's not exactly correct. Yeah, you can say prefix of r minus prefix of l mod 100, right? Okay. So I'm just directly got into prefix, but you can also say this is nothing but a of I from I equal to l to r mod 100, right? Get this summation first and then take a mod, right? This is going to be the final value. Is this clear to everyone that for a range L to R, if we are merging the elements AL plus 1, AL plus 2 and AR, the final value is going to be this summation mod 100, because this property is going to hold true, right? This is what we showed, that for three elements, if this is working, again, if you do one more element from any side, whichever side you want to, anywhere in this tree, it is going to just come out to be A4 plus everything rest, right? So this is going to hold true. Right? So in fact, in this problem, when we had to merge from L to R, we knew what the final value of x was, right? We knew what this value is. Okay. So whenever we have to merge from some x, like some 8 L to R, we know its final value is going to be this particular expression. Okay, sum mod 100, or you can calculate it by prefix sum in order 1 if you want. Okay. So now, how do we now solve the problem? Like, this is all just two observations that we talked about. That first was, it's going to be some mid breakup happening in the array, split up in the between, and L2 mid is going to give me some element y. Mid plus 1 to r is going to give me the like another element z finally, and at the last step they are going to get merged into a final element. Okay. Now, if you think about it, if we note the mid, the value of y, z, and x are all fixed, right? Value of y will be nothing but like this particular range sum mod 100. This is z is going to be this range sum mod 100, and x is going to be the whole range sum mod 100. So I have written it y, z, and x, but they are actually fixed if you think about it. Okay, but this mid is not fixed. We don't know what this mid is. Okay, make sense? Is everything clear up to this? Okay, so now we don't know what this mid is. Okay, so what we will do is we will iterate on all possible mids. So mid can take from L to R minus 1, right? That is the only possible splits that can happen. Okay, so we will iterate on all possible mids that can happen. Okay, we will iterate on all possibilities. Okay, and whatever the mid value is, we know that to reduce this much range, the maximum reward that you can collect is going to be dp of L2 mid, right? This is the maximum reward, and this final value is fixed. So whatever you do, the final value is fixed, so it does not depend on that. So this particular value is going to be equal to prefix of mid minus prefix of L minus 1 modulo 100, right? This value is going to be this, okay, which is, let's call this y. Okay, similarly, when we are merging this much, we know this is going to be the most optimal, the maximum profit that you can create. So we know the like final value is fixed, so we will just have to decide the order in which we do, so that the profit is maximum, right? So the profit will be maximum when using this particular recurrence, because dp calculates that only, what is the maximum profit that you can get by merging this whole range into one element, right? So this is going to be equal to mid plus 1 to r, right? This final element is fixed, that is nothing but p of r minus p of mid mod 100. Okay. Okay. And we know that if we merge these two, we will get, the value is anyways known, so we don't even need that to calculate dp of L. So this particular merging will give us a reward of y into z, right? This is going to be the reward. This is z, this is y. Okay. So in total, if we split at this mid, okay, our reward is going to be this plus this plus this, right? So reward for merging all of these into one element, that's all reward is calculated by this. Merging all these elements into one element, all that reward in this, plus this final merging reward is going to be this, right? So this is for one possible mid. Now we don't know what is the most optimal mid, so we will iterate on all possible mids. So we will loop on mid from like L to R minus 1, right? At least this has to be one element, right? On this side. So up to R minus 1, we will loop on mid. And for all of those possible values, we will have to like find out the best. Out of all these, we will take the best mid. Like whichever mid gives us the best value of some of these three values. Okay. Does this make sense? Is this whole idea clear to everyone? Anyways, we are going to implement this one, but still the idea should be clear that why is this even working? Okay, so there are two levels of observation that we need to first of all understand in this problem. That this summation property, that it is always going to get merged into this a fixed value, and the next one is there is a split that will happen. There is a mid that you can find such that all elements before mid got merged into this, all elements after mid got merged into this, and then they finally got merged, right? So these two things are holding true in this problem, and that's why we are able to make this kind of split. Okay, is it clear to everyone? Can I have a +1 if it's clear to everyone? Like this should be clear by now. If you have a doubt, you can ask. Okay, so that's all how you calculate for L2R, and in like the answer would be equal to dp of 0 to n minus 1. Like let's say I'm taking 0 indexed. So that is going to give me the answer in range, let's say 0 to n minus 1. That's like reducing the whole array. That's the best you can do, right? So that is going to be my answer finally. Okay. So let's quickly move on to implementing this particular idea. Just have to draw something. Okay. So I would be implementing it without using prefix sum. So you can calculate the sum efficiently. So let me start with the implementation and I will explain things as we go ahead. Okay. So we are first of all given the like n and the array, right? So that of course goes without saying that we need those things in the input. So array could be of size 500. So I will take up to this. Okay. Scene n for integer I equal to 0, I is less than n. Scene error of I. Then we are doing memset. So we will keep a global array dp. So I'm going to just reset that. Okay, so this is how you use memset. Now you just need to find out. Let's say I will keep a dp, which will need me to like for every possible L2R we need to calculate. So it's going to be a 2D dp. Okay, and let's say recurrence gives me like the answer from L2R. Okay. So recurrence of 0 to n minus 1 is going to be my answer. Okay, that's all. So now we need to complete this recurrence part. That how do we calculate the answer for L2R range? Make sense? Now, if L is equal to R, okay. So what is the base case for this? If L is equal to R, what is the cost to merge single element into one element? So what is the maximum profit that you can create? 0, right? It's not ARR of L, it's 0 because there is no profit that you can generate by merging one element into one element, right? So we just return 0. That's the base case. Now if dp of L comma R is equal to -1, okay. So in that case, it's not calculated yet. So we have to calculate the answer. So we will keep an answer equal to 1e9. So we will try to do it in the most optimal way possible. So we are okay. So we need to make it maximum. So I'm assuming that things are all positive. So all the time the cost will be positive. So keeping a answer equal to 0 is sufficient, or else we could have kept it negative as well. Okay. So answer is always positive. That's why we can use dp value equal to -1. Okay. Now we will keep some sort of total, which is like total sum of the range. Okay. So I will explain why I'm keeping this without using a prefix sum. It's just another idea that you can use in some problem without building prefix sums. Okay, so we will just create the total value of the range. Okay, so we are just adding up the range. That's it. Okay, now we will create like running sum. Okay, and now we will loop on all possible values of mid equal to L, mid is less than R, mid plus plus, right? So we are basically iterating on all possible mid values, and we will maintain a running sum, that what is the sum of elements on the right hand side. Okay, so this is the sum of elements. If we keep on doing this sum, it will maintain me the sum of elements on the right hand side, right? And the left hand side is nothing but total minus sum, because we know the whole L2R is total and this particular part is sum. So right hand side is total minus sum, right? So that we can find out using. So now let's talk about answer. So answer is going to be min of any previous answer, or either you like break it down at mid. So that is going to be L2 mid. Okay, whatever is like optimal for L2 mid. Okay, this is going to be max, because we want to maximize the reward, right? Then mid plus 1 to R. Okay, plus whatever the sum of left hand side is, mod 100. Okay, this is going to be the actual value of the left hand side, multiplied by tot minus sum, that is going to be the sum of right hand side, mod 100, right? These two sum is, and the product is going to give us the value. Note that I've not written mod 100 over here, rather inside, because this product is going to happen with these values, right? It's not product mod 100. So keep in mind that it's not product mod 100, but individual mod 100 is product. Okay, there's a difference between the two. Okay, and now once we do this, like once we know the answer, we just have to save it to some dp L2R. Okay, so next time it's going to be this answer, and then we return dp of L2R. That's it, and that's the whole code for this particular. Make sense? So a quick base case for range L2R. If it's not calculated, just iterate on every possible mid that you can create and calculate the answer, and that's it. That's, you are done with dp of L2R. Okay. Is this clear to everyone? Can I have a +1 if this code is clear? If you have any doubt on any line, you can ask that. So so we on the previous day we discussed a very simple problem of LRDP. Okay, this is something called LRDP or interval DP. Okay, LRDP or interval DP. As the name suggests, like you keep the answer for some interval L2R. Okay, so this is one of the class of DP problems that come up. Okay, and it's quite important. Like a lot of problems can be solved with LRDP and interval DP. Okay. Makes sense? Okay. So now let's get back to the problem. Mid should be from L to L plus 1, from L. Yeah, so L to mid and then mid plus 1 to R. So I think it's correct, right? Because like it's L to L, like L to L is one element and L then L plus 1 to R. So this is one possibility. It's not up to R, because then this particular element would have got to like R plus 1. That's not possible, right? Not taking prefix sum, that's just there's no reason, like you can do it with prefix sum as well. So the thing is, it does not depend, like the complexity does not change, that's it. Like now we will talk about the complexity of this, but you can also keep prefix sum, like it's no problem. So we are doing some sort of prefix sum over here. It's like not prefix sum, like running sum of left hand side and subtract to get the right hand side and so on. So what is the complexity of this code? Can any one of you quickly tell me that? Okay, so organizer says order n cube. Anyone else having any other idea? Okay, so it's order n cube because using the same idea that number of state is order n square, right? There are n square number of states, and for every state there is an order n over work over here and order n work over here. Okay, order n transitions over here. So in total, like this total, like for every state the computation takes order n. So it's number of states multiplied by average number of transitions. That is going to be order n over here, and that is going to be order n to the power. Makes sense? So it's n cube in total, and the n cube works well with 500. Okay, 500 cube works well. Okay. So if you see a problem with constraint like 500 and something, it might be a it might be a good idea to use uh, interval DP. When to use recursive or iterative DP approach? Uh, till the 8th week of this such like this practice, I would suggest you to use recursive DP so that you build the recursion intuition. It takes time; it's not very trivial. So keep using recursion, but till now, by now, like as long as you can. But after that, you can also code these problems with an iterative style. Like once you get fluent with these things, you can use iterative DP. But it's like coding recursive ones are comparatively easier because you don't have to think about dependency and other things. Like it's just simple recursive calls, right? It's going to give you the correct value. In iterative, you have to think about how to write the loops and other things. Of course, sometimes code become much easier to write in iterative fashion. That's why a lot of senior, like when you get at the senior levels in competitive, people use mostly iterative only. But still, recursives are better to learn DP. Okay, so stick with recursion for now for most of the problems. Uh, Once you feel like okay, I'm confident with recursion, I can always write a recursive DP. Then you can try on writing iterative DP. It's completely up to you, but I would suggest stick with recursion right now. Okay. Like in this problem, if you are writing in iterative style, you need to know how to write iterative styles for like LRDP. But once you know, even that becomes easy. Like it's not something very difficult. So if you ask me, I in competitions mostly use iterative, but uh, like both are almost equal. Like there is no big advantage that you would get. Okay, it's just easier to understand the recursive one, and it's easier to like it's shorter to code the uh, iterative one. Okay, makes sense. So now we will be moving to the next problem then. So the next problem is more or less the same problem. Okay, again there is an array given and you have some sort of like uh, let me give you the exact statement that you are given a same like n sized array a1 a2 a3 a. Okay, and now we just change one thing that now when we merge, say there is same constraint that you can merge any ai and ai plus 1. Okay, when we merge these two, you get a so whenever you merge, you get a profit of like the same thing. Let's keep it the same. Okay, you will get let's say you will have to pay a cost. Let's change the question a bit just to change min and max. You need to pay a cost of let's say ai into a of I plus 1. Okay, this is the new, this is cost now. Okay, so reward is used to like you need to maximize reward and minimize cost. That's the only general notion in any problem. Okay? So when you merge two neighboring elements, you get a you have to pay a cost of ai into ai plus 1. Okay, and you will get a new element which is equal to ai multiplied by some capital X plus AI plus 1, whichever element you are merging, okay, multiplied by capital Y plus Z mod, let's say 50, okay, mod 50. Makes sense? So these X, Y, Z are fixed in the question. Like there are like X, Y, Z are fixed throughout the problem. Okay, so it's like uh, three constants. Okay, and the problem is same, that you have to like merge all elements. So find out the minimum cost to merge all elements. Right now you have to minimize the thing. Just it's just same, like it's changing min and max. But anyways, the idea changes a bit. Now you need to make the whole array to one element with minimum cost. Find out that minimum cost. Okay. Is the question clear to everyone? That okay, the question is more or less same again. Like if I make X and Y equal to 1 and Z equal to 0, the question becomes the same problem. Okay. But now I'm saying that okay, the merged element will depend on some X, Y, Z input. Okay, it's not always same. Now why is this given? More like if you think about it, why is this XYZ given? Now the property that we talked about, that A1 merging with A2 and then merging with A3, it will depend on how they merge, right? Because in this it will get multiplied with X, Y, and plus Z is there, and then this gets multiplied with X, this gets multiplied with Y plus Z. But now if I some change the ordering, the final element is going to get a different value, right? So that's the only change that happening, that okay, now the final element value is not fixed, so some sort of, okay. So now find out the minimum cost in which you can merge all the elements. That like the question remains the same, just it's just the observation that we talked about earlier, that okay, it's going to merge into this value is not going to hold anymore, okay. Now let me give you the updated constraints. So constraints are a bit smaller. So now we say that okay, let's say n is up to 50 only, x, y, z, a of I all are less than 50. Everything is less than 50. So since it's small 50, will brute force work? Well, in general, like, can someone quickly tell me what is the total number of ways in which you can do these merging operations? Like, what is the like if you brute force this, what is the number of different possible like mergings that are possible to finally merge it into one element? Like how many different orders of merging are there to merge it to one element? Can somebody give me a quick number on that? Like some complexity. N factorial. Yeah, it's not n factorial, it's actually n minus 1 factorial, but that's okay. So you can think about it in terms of this, like okay, there are, let's say there are n minus 1 boundaries between the elements, and in each move you have to remove one of them, right? You have to remove one of them and the elements will get merged. So it's like permuting this n minus 1 boundaries, so that is going to be n minus 1 factorial, right? So it's like it's bounded by factorial, so of course you cannot use brute force in even if n is small 50, okay. No brute force, no meet in the middle will work, because for factorial it has to be less than like around 12, 13, then only it will pass. Even 12, 13 is quite large. 10 should be good enough. That's the highest you can go for factorial. So how do we solve this particular? Like what would be our DPs? Of course, we are talking about DP today, so this is also a DP. think in terms of DP, that what is best to keep in this particular problem. Any ideas? Any random guesses? What can be the state? Like it's like LR cost can be pretty large, so keeping that in state won't work. Something smaller, LR merged value. Yeah, this time we need to keep LR comma merged value. Like what is the, so this time what we will keep is for L2R. Okay, if we merge it into some value, let's say X, what is the minimum cost? Minimum cost to merge the segment L2R into a value X. Now this might not be possible. Okay, this might not be possible that you can merge that. It's not feasible to merge it into X. So in that case, this is going to be some infinite cost. Okay, like if not possible, then the cost is infinite. Make sense? So this kind of state is something that you will have to think about in most of the problems, that what do you keep in state so that you can calculate the answer. Okay, so if you remember in the earlier diagram that we drew, that okay, we have some sort of array and we were breaking at some mid, so this got merged into some element y, this got merged into some element z, and then this got merged into some element x, right? So earlier we knew the value of y and z for fixed, right, that these are the possible values. But let's say we don't know that. This time it's not fixed, so we will try to iterate on all possible values of x and y and z as well, because y can also take only 50 values and z can also take only 50 values, right? That there are only 50, like everything is mod 50 in this problem, right? It's everything is mod 50, so every number is going to be less than equal to 50, less than 50 in fact. Okay. So it's always like up to 50 only, so we'll try to iterate on every possible value over here. Okay. So if you think about it, like let's say we want to merge the segment L2R. Okay, so we will try to use every possible mid. Okay, and if we use this mid, we know that okay, this will get to some value y. Okay, so we will try to use all 50 different values of y possible. Okay, this will merge into z. We will try to use all 50 values of z possible. Okay, and we will try to fuse it into this x value. So the final recurrence is going to be something like dp of LR comma, so x is going to be equal to y times, okay, the naming has got a, okay, it's, let's keep this, okay, we kept this xyz. Let me use some other color. Okay, this will go weird. Let me just quickly use ABC for this, like just for now. Okay, these are the three constants. They were x, y, z, but I'm not just writing them ABC. Now they, if it's y and z, it's going to get merged into this value, and this this dp will get update, like one possible value of this dp is going to be dp of L2 mid. Okay, plus, sorry, L2 mid to Y, that is going to get into merged into Y, plus dp of mid plus 1 to R with a value of Z finally, plus Y into Z, right? This is going to be the possible. This is going to be one possible update. Make sense? So this is the value of Z by our expression that we decided. Okay. But there are still some difficulties in this like code. When we try to implement this, there is a difficulty because when we need to calculate some possible LRX, right? So we know that this value is X. So how do we efficiently iterate on? So do we iterate on every possible L mid and R for every X? Okay. What I mean to say is, like, to calculate the answer for L, R, and X, do we iterate on all 50 values of this range and this range? Because we know that we can optimize a bit over here, that okay, there are only 50 values possible for this L2 mid. Okay, for this mid plus 1 to R, there are only 50 values possible. Okay, and then they are going to get merged. Now this X can only take the potential values that can happen by merging these optimal values only, right? So instead of calculating dp of L, R, X individually, we will try to, like, whenever we see some L2R, we will calculate the dp of LRX for all possible X in that range. Like, all, what is the answer for all 50 values over here? Like, what is the best possible way to merge this L2R into all 50 values? Okay. In that case, we will try to iterate efficiently on these two values. Okay. Makes sense? So the problem that was happening was, if we try to calculate every possible LRX by iterating on all Y and all Z and all mid, so the complexity would have been, like, there are three states, so it's 50 cube multiplied by, there are three iterations that we are doing, one on mid, one on Y, and one on Z. So it's 50 cube, right? So this is going to be 50 to the power 6, which is very large. This is not going to pass. So the optimization that we will use is this X. We don't have to calculate the answer for this state. We can calculate the, like, we have to calculate the answer for this, but we will try to calculate the answer for all fixed LRs, all different values of X together by iterating on 50, these 50 and this 50 value only once. Okay. Now what I'm saying right now will make much more sense when I code this, but this is some implementation optimization that I'm doing right now, that I can reduce this particular part to this much, which is going to be sufficient enough to pass, because there would be some divide by 2 and other things. So this is small compared to the previous one. Okay. Is this idea, like, is this recurrence making sense right now? Is this recurrence clear? Forget about this iteration and everything. Is this recurrence making sense? How many of you are, like, clear with this recurrence? Can I have a +1? Why is this recurrence working? So we're basically looping on every possibility that we can do, right? Earlier we looped only on mid. This time we are also looping on Y and Z, because we don't know what these will get merged into, right? So we will try to loop on every possible merge value as well. That's it. Is this recurrence clear to everyone? Can I have a +1 quickly, and we can move into the coding of this? I will code this one so that it becomes clear. So I'm just removing this part. We need to change some of these things. Okay. So just changing, let's say X, Y, Z is given as inputs, right? X, Y, Z is given us as the input. Okay. Then we'll try to merge it into some value, let's say X. Okay. So this is what we want to merge it into, this value. Okay. What is the optimal cost for this? So now what we will do is, again we will write the same recurrence, that if L equal to R. In that case, what do we write based on this X? Can someone quickly tell me? What is the cost to merge it? What's the cost of merging a single element into some value XX? Not Z. 0 or infinite, right? Either of them. So if ARR of L is equal to X, so then it's like returns 0 because you don't, it's already X, so you don't have to do anything. Or else, like if let's say there is one element and it's not equal to XX and you have to merge it into value XX, so that's not possible, right? So you return 1E9. That's not possible. Make sense? Now if, so we will create a done array, of course. Like we will create a boolean done, that is the range done. Okay. So this time we have only 50 values. Okay. Like n size was 50. So if my L2R has been calculated before, like if my L2Rs, all different value of X has been calculated before, I will just return whatever the, let's say I will create another array. Let's say some memo. Okay, so let me rename a bit. I will call this DP and I will call this memo, because I will be using the same recurrence so that it becomes clear to you. Okay, so all these different values are going to stored in memo. Okay, so I will just return the memoized value of LRX because I have already calculated this LRX once. Okay, so for a particular L and R, I will solve it for all possible values of X and store it all together at one go, so that next time I don't have to calculate everything. Okay. Now, what I will do is I will loop over first. Okay. So now, if this is not true, then I will have to calculate it, right? So what I will do is I will loop over all 50 values for this particular range, and I will say that, okay, I need to calculate the answer for L2R. So let's say memo of L2Rs. I initially don't know whether it's possible or not. So to merge L2R into some value I, let's say it's going to cost me 1E9. Okay. And then I will try to loop on all possible mids equal to L. Mid is less than R, mid plus plus. Okay. For integer, like let's say Y value, sorry, Y is now input. So let's say the first half, the first segment, okay, it can take up to 50, right? Let me explain what this fs is. So this y over here that we wrote is the fs, like this is going to get merged into some value fs. Okay, so we are basically writing this element as fs, this element as some, let's say ls. Okay, and this is going to be the cost to merge it into ls. So mid plus, so this cost is nothing but mid plus 1 comma r to value ls. Okay, this is the cost to merge it into ls. To merge this into this is going to be equal to dp of l mid comma fs. Okay, and then finally merging this. So that's this part. Okay, so we are iterating on all possible values because one of the optimal, like whatever is the optimal value, we will get that from merging some optimal value only, right? Okay, and memo of L2R is going to memo LR and then this fs into x plus ls into y plus z whole taken mod 50, like this is going to be the final merged value, right? So that particular memo value is going to get updated by minimum of whatever the value initially was. Okay, and the three terms that we have in the cost table, dp of L2 mid comma the first half. So we are going to reduce the L2 mid into the first value plus dp of mid plus 1 to r into second value. Okay, that is nothing but ls plus fs into ls, right? Make sense? So this is going to calculate everything in the range L2R, and then we will say, okay, dp of L2R is now done. Okay, all values. So with these three loops, all different values of dp of L2R has been calculated. So I say that, okay, the range L2R is done, and then I will return the memo value of LRX. Okay, make sense? And that's all for the recurrence. Now, how do we calculate the answer? Any ideas? How do we calculate the answer? Okay, this is going to be done of LR. So how do we calculate the answer for the whole problem? That what is the optimal cost to merge it into one element? The minimum cost. So the final merge value can be anything from 0 to 50, right? So that's what we will loop on. Okay, answer is equal to min of dp of, you have to reduce the 0 to n minus 1 into, let's say, some value I. Okay. And you take it with any all the defect maxes. Okay. And just need to print that particular answer. Okay, that's it. Okay, is this clear? That's all. So there is this. So this is the idea that whenever you have some sort of like combination that you are not able to keep track of, just put that in recursion and try to loop on things. Like it's possible that since the ranges are small, you can loop on different values that it can take and somehow combine that particular value. Right? Yeah, we will explain the time complexity anyways. So what what is the guess of like time complexity? I think I have already told the answer. What is the time complexity going to be? But like if you think about it, this particular xx is not playing any role in calculating the state, right? We are only calculating every l comma r once, right? Every l comma r once, and for every l comma r we are doing a order nq operation. So if you think about it, this xx is just a parameter. It's not being used as a like it's not going used. It's not that for every xx we are calculating separately, right? Yeah, the answer is always greater than equal to 0, right? It's because its product is going to be greater than equal to 0. Now for every l comma r we are keeping a done table, that is that l comma r done. If it's not, then we are calculating the answer for that l comma r, right? So for every l comma r we are doing a order n cube computation. So an l comma r can take order n square different states. So in total this is order n to the power 5. Okay. Well, it might seem to you that okay, there are 50 values over here that are also there, but it's not like it's not computing this n cube operation that is over here is not happening for every different x, right? It's only happening once for every l comma r pair. Then all different x value has been calculated, whichever are reachable, whichever are not reachable by this expression is going to remain 1 in 9, like not possible, infinite, right? 1 in 9 is infinite cost. Make sense? Is this clear? This is going to be order n to the power 5. So how many of you are like clear with this particular code? Can I have a +1 quickly on the chat if this is more or less making sense? Okay. So anyways, this will be there in practice problem. So you'll have to code this problem once. Yeah, so that's why we are using done of l comma r, because every l comma r is being done only once. That's why we are marking that separately. Okay. Yeah, exactly. Is this clear? Okay. So let's then move to the next problem. So this is now a fairly like a standard problem. The previous two were not very standard, but let's say this in this particular problem, you have some given expression. Just a second. Yeah. So you have an expression given to you. Let's say 3 plus 2 minus 5 multiplied by 3, so on. You have to put in brackets onto this expression so that this evaluates to the maximum possible value, right? So just a second. Yeah. So in this particular expression, you have to put in brackets so that you can get the maximum possible expression, maximum possible value. So let's say in this expression, if I think about it, it's rather difficult to directly get the answer, but I think the best way would be to do this, or else it's always negative, right? And then you have to parenthesize this. Okay. So this is going to give me 0. You can try out parenthesizing it with any other order, and you will see that, okay, it's going to get negative. I think so. Okay. Is there any better way? So given this sort of expression, like you are given this 3 plus 2 minus 5 multiplied by 3, find out the like way you put in brackets over here so that this particular expression gets its maximum value. Uh, yeah, that's more or less correct. But like, what is the thing that you save in DP? Yeah, so we have to keep both max and min. Okay. So this is again like more or less the same state if you think about it. Okay. Okay. So so if you think about it, like there is some operation like operator over here, and then there is some number over here, right? Operator over here, some number over here, operator over here, some number over here, and so on, right? So let's say these are the like this is the range that you want to first of all like parenthesize, and this is some range L to R. Okay. So in that case, we will have to like try to bracket it out. Like this particular like whole expression can be thought of like there is a parenthesis over here, and there would be a final level parenthesis, right? That okay, some like continuous range, something like this is going to get merged, something like this is going to get merged, and they are then finally going to get this particular operator, right? Okay. So this is also more or less the same type of state that you're thinking about. Okay. Now the catch over here is you just if you want to find out the max of the range L to R, okay, what is the max you can get for the range L to R? It's not just max that you will have to store, you will have to also store the minimum that you can get for a particular range L to R. Okay. Now why is that? Now this particular like part will get evaluated into some value over here. This will get into some value over here. And then there will be this operation, whatever operation is over here is going to happen between these two elements, either plus, into, or minus. And then this is going to give me one expression or one value, right? This is what is happening. Is everybody able to see this particular setup that this is going to happen in this particular expression? Can I have a plus one if you can understand that this is like this bracketing is going to give us the same type of scenario in the as in the previous problem, that there will be some continuous values that is going to get evaluated first, continuous value into one, and then this some operation will happen last, and that particular operation is like this plus into minus. Okay. And that is going to give me this expression. Okay. Okay. Now let's talk about plus. So if we want to like maximize this final result, so it's of course better to take this and this max, so that when we add it, it's going to be maximum possible, right? uh, let's say when we have to do like some a and b is there, and we have to do a subtraction, okay? So in that case, what is the optimal way? We have to keep a track of the maximum of this and minimum of this, right? I hope this is making sense, that if we want to like maximize this whole expression, like this x, we have to maximize. This has to maximize and this has to minimize, right? Of course, I think this is true. So we will try to keep the max of this range and the min of this range, that is reachable, right? For subtraction. What about product? Now product is a bit different. So since the results can be negative and positive both, when you have a product between a and b, okay, when they are both positive and both negative, then we will try to take its maximum, right? Maximum absolute value. And when like one of them is positive and the other one is negative, so we will try to make it as minimum as possible, right? So how do we do that? We can sort of like try all possible combinations of their max mins, okay? It's going to be one of them all of the time. Makes sense? So what is the like when we have to try to take the product, like take all four possible combinations, that max with this min, max with this max, min with this max, min with this min. So this will take, so there are multiple possible cases that can happen, that like both the max are positive. So in that case, of course, multiplying them will give us maximum. If both the min are negative, then both multiplying them is going to give us a potential value. If that is not true, that like there is something like this, like all this particular b is always negative and this a is always positive, so in that case this minimum and this maximum will give us the answer, right? Like this max is like smallest negative and this is smallest positive, so their product is going to give us the smallest negative number possible. So that's what we are trying to do, okay? So out of these four combinations is going to give us one of them is going to give us optimal, right? So that's what we will do in this particular problem, that when we try to implement this particular thing, what we will do is, okay, I will loop on all possible mids, like up to this is going to be first, mid plus 1 to r is going to be the second, okay? And whatever I reach at, like there are two possible values over here, min and max, okay? There can be two possible values over here, min and max, okay? And I will try like all four combination, like I will just try all four combination with this operator, whatever operator is present over here in between min and mid, okay? And that is going to give us like the min, like out of these four combinations, whatever is minimum is going to be this element's minimum, and whatever is maximum is going to be this element's maximum, okay? So this particular problem teaches us one thing, that whenever you need to just find one possible value for dp, it's not just always the case that okay, I need to keep that same value as the dp, okay? You might need some auxiliary information along with that particular value to construct the value for like bigger range, right? So for the smaller ranges, from these smaller ranges, you needed both min and max to calculate the min and max for the bigger one, right? If you keep just max, it's not possible to construct the max over here, okay? So in some dp, okay, there are a lot of such problems. It's not just one, but it's not just sufficient enough to keep just one thing that the dp is returning. It might return more than one value, right? The only condition that it needs to hold is the bigger problems optimal values, like whatever you are keeping, like min and max both, they should both be constructible from min and max of the smaller ones, okay? So that's like overlapping sub problems mean that the smaller sub problems the optimal substructure, there is a property of optimal substructure in dp, right? That basically means this, that optimal values of smaller ones can construct the bigger ones optimal value, right? And that's what we are having over here. It's not like there is some value between min and max that is going to give us best with this, okay? It's never going to happen like that, okay? Is this clear to everyone? So this is more or less the same, so I'll not be implementing this one. It's just same, like you just have to loop over every L2 mid, and mid plus 1 to r. So you can think about like when you go about implementing this, you can say that okay, dp of l comma r will return me two values, min and max, okay, of the range that are possible, okay. And for any particular, to calculate this value, we will loop over every mid. So we will loop from L to mid. From this, we will get two values, min low and max low. And then from mid plus 1 to R. From this, we will get, let's say, some min high, max high. Okay. And then we will, whatever the symbol is over here, like let's say product is over here. So we'll try all possible 4 products. Okay. And from all those 4 values, take the minimum as the global minimum and take the maximum as the global maximum. That's it. Okay. That's going to give us the best possible answer. Make sense? Is everyone clear with this? Can I have a +1 on the chat if this is clear to everybody? I think it's not a big thing to implement. Like it's more or less same as the previous problems. Okay. Is this clear with everyone? Okay. So this is one style of LRDP. So we have been taking up this more or less quite some time now, that you have to break the L to R segment at some mid, and that is going to give us the answer, right? Okay. Now let's talk about another problem now. This is an interesting one. Let's say you are given some array. Okay. Let me take up one example, and that should make things much more clear. Okay. So let's say you're given, so what we have is something like this. Like let's say there is a array something like this. Okay. 1 3 3 3 1 1. Okay, something like this. So from this array, what you can do is you can take up any like sub array which has all same elements. Okay, and you can delete that sub array. Okay? So you can find one subarray which contains all same values, and you can delete that element. Okay, that subarray. Now let's say the subarray had k number of elements. Okay, let's say there are, in this case, k equal to 3. Okay, there are 3 elements. So you will get a reward of 3 square. Okay, in fact you will get a reward of k square. Make sense? So you just reduce any subarray into like null if all of them are same value, and you get a reward of k square. Okay, after deleting this, the left side and the right side get merged together, and you will get this new array, right? Then you can delete all these 4 array elements into one, into nothing, and you will get a like a reward of 4 square. Okay, and finally you will get to null. So you have to delete the whole array by using these operations, such that the sum of reward of every step is maximum. So you have to find the most optimal way to do this. Okay, so let me give you one more example. I think that should make things much more clear. Okay. So basically you can delete any subarray with all same values. The length of the subarray is square of that is going to be your reward. So find out the maximum reward that you can correct by deleting the whole array. Okay, you have to delete the whole array at the end. Find out the maximum price that you can correct. So let's take one more example. Let's say this 1 3 2 2 2 3 4 3 1, something like this. Okay, so what we can do is we can maybe delete all these. Okay, so you get to 1 3 3 4 3 1. Okay, and then let's say I delete this 4, so you get 1 3 3 3 1. Then I delete all these 3, so you get 1 1, and then I delete 1 1, so you get to null. Okay, Now this is going to give me 2 square, this is going to give me 3 square, this is going to give me 1 square, and this is going to give me 3 square. So the sum is going to be equal to 9 plus 1 10 plus 9 19 plus 4 23, right? This is going to give me a total of 23 points. 23 score. So you have to maximize this. Make sense? Is the question clear to everyone? Can I have a plus one if this is clear? Because this is something we'll be discussing for a while now. So it's important that this is clear. So how do we solve this particular? Any ideas? So of course we will look into DP ideas. What kind of state can be used in this particular problem? Or first of all, will greedy work in this? Like greedily removing the best one. It's so in these kind of problems, it's not like it's mostly not the case that greedy works, because there is a lot of choices that you have in the problem, right? Like from where do you delete what, and then again sizes can keep increasing, right? So there is a k square cost that's also not linear. So it's not like possible to do a greedy in this problem. Like if you have like at multiple places the highest number of frequency that is continuous, so which one do you delete? It's not possible to decide, and even in that case, right? So greedy doesn't generally work in these kind of problems. Okay, so how do we even write a DP for this? Like what can we do for DP? So out of the things states that we talked about, what is like a possible state that we can keep in this problem? Any ideas? Any guesses? It's also take some time, take 1 minute, think about it. What can we use? So which type of state is like you're thinking in that can be feasible for this one? Any guesses? Like right, there are only 5, right? So there is like on worst case you can, and we know it's not a game. So 1, 2, 3, 4. Just take a guess, right? Okay, 3. Right. So out of all these states, it should come to you naturally that okay, this is not going to work. This is not going to work. This is mostly for strings. So this is what we are talking about, right? So that's why it's not very difficult to think about states in DP, because there is a finite list of states that can happen, like finite list of base states that can happen. Of course, we need to augment it to satisfy the problem, but like the basic idea that you need to think is almost this 5. Okay, there will be more. We will be taking up more type of states, but there are these 5. Okay, now how do we extend on this DP of L comma R? How do we extend on this? but like of course L2R, just keeping L2R is not sufficient in this problem. Like it's not that trivial, because what do you keep, like what is the answer that you're building with just L2R? Okay, so let's look into how are we doing this. Okay, so let's take this example 1322223. Okay, something like this. Let's say this is my L2R. Okay, let's take just this part. Okay, let's say this is my L and this is my R. This is what I'm calculating for now. Okay, so I'm trying to delete all these. So I'm thinking in the direction that what is the best way to delete L2R. Like I will delete the range L2R and I will get the maximum profit. Okay, maximum profit that I can make by deleting range L2R, which seems quite natural, right? This can be a potential state. Okay, what is the maximum profit that I can create by deleting the range L2R? Okay, now when we have to delete the range L2R, think of this first element. Okay, concentrate on this first element. How can this first element get deleted? Either it will be deleted alone, like it is not going to get merged with anything else. Okay, now when we are talking about L2R, there is nothing before it and after it. Okay, so we are only considering this L2R. Okay, it's going to get deleted like independently. Okay, so talk about this first three. Either this three will get deleted alone, or this three will get merged with this three, right, and then get deleted. Okay, or else this three will get merged with this three. Okay, or it will get merged with both of these threes, like, and the rest of the things will get deleted, right? These are the only possibilities. Okay, so let's think about this particular case, that this three gets merged with this three. Okay, I mean to say this three is going to like get deleted along with this three. So in that case, to get this three up to this point, like to get it beside this three, all these have to get deleted, right? Okay, and that is going to be just another DP call. What is the optimal way to completely make this disappear? Okay, L plus 1 to whatever this x is, x minus 1. Okay, make sense? So if we want to merge this three into this three, we have to delete all these things in between them, right? This is, and the optimal way to do is given by this DP, right? But there is a problem that okay, this tree might not just get deleted after this much tree. It might get deleted after like this 4 gets deleted and these all 3 get merged together, right? This is one possibility. One more possibility is there, that okay, you don't even you even delete just this tree, like you delete all this range and this tree gets merged with this tree. This is also possible, right? Makes sense that this tree might get merged with this tree and this gets deleted independently, because this gets deleted over here in this subrange, and then this gets 3 gets to this 3, right? This is also a possible case. And then the third one was like these all 2s and 4s get deleted and this 3 and all these 3 get merged together. Like there are more or less, like if there are like n 3s over here after this 3, so there would be 2 to the power n choices, like which all 3s are going to get merged with this 3. Okay, and that is pretty large. It's not possible to handle every case using some sort of version. Okay, it's not possible to handle 2 to the power n. So we will need to augment the state a bit to handle these things efficiently. Okay, so let's understand how will we do that. How will we do that? That is pretty much the trick in this problem that you will need to know. It's not very trivial to think about it. Let me quickly erase this and I will write this again. So let's say there is this 3, 2, 2, 2, 3, 4, 3 that's there. Okay, that is this L2R. Okay, now I will change this state a bit. I will add K over here. The another problem was, even if you had to decide on which one to merge, the number of 3s that are there is going to matter, right? So we will add this key over here so that it tells me, okay, I have L2R and the first element appears K extra times. Okay, the first element appears k extra times. Let me explain what this is. So basically now this dp of LRK is going to be equal to the max profit that you can get from the range L to R, such that initially there was k extra elements of the first in the beginning. Okay, so initially over here there is no extra. Okay, now let's say I decide that I will merge this 3 with this 3. Okay, so in that case what I can do is I can delete this range. So that is going to cost me, let's say, this is going to be, let's number them. Okay, I'm just quickly, anyways, instead of saying them L and R, I'm going to number them 1 2 3 4 5 6 7. Okay, so to delete all these elements, it is going to cost me dp of 2 to 4. Okay, this is going to the cost of deleting all these, and there is no extras, like there is no extra that I get in this. Okay, now when I want to delete this 3 along with this 3, I have this much range left, right? So I will call dp of 5 to 7. I have to delete the range 5 to 7 with one element extra. What is this extra? This 3 is going to get merged with this 3, and now when I am considering this range 5 to 7, the first element appears one extra time. Okay, this is what this extra key that I'm introducing in the state means. Let me explain this. Okay, now let me talk about another possibility that is there, that I will not merge this 3 with this 3 but with the other 3. Okay, this 3. So in that case, my dp, so everything in between needs to get deleted independently, so that then only I will get this 3 beside this 3, right? So this is going to be dp of I need to delete 2 to 6 with no extras, plus my last, like up to 6 I deleted. So from 7 I have to delete up to 7 with one extra. This 3 got extra over here, right? Okay. So now these two cases are possible, to merge this 3 with some next 3. Now where did this possibility go, that I delete all these 3 together? So if you think about it, that is getting handled in this particular case, because when you call dp of 571, that basically means that you are trying to solve this particular part, that there is a 5 7, like 5 to 7, so there is this range. Okay, and then 3 has one extra 3 that is hanging somewhere. Okay, this is 5 6 7, indexes are 5 6 7, and there is a extra 3 that is hanging with this 3. Okay, they are going to get deleted together. And now for this 3 there is a choice that, okay, this 3 gets independently deleted. Okay, there is one more choice that I forgot to write over here, that this 3 gets independently deleted. That is nothing but dp of 2 to 7 with no extras. Okay, that's all, one more possibility. Okay, so there is one possibility that this is going to get deleted, and this everything you have to delete. Okay, dp of 6 to 7 is something that you will have to delete, or else what you have to delete is, I'm not writing the cost right now, that what is the extra cost that is coming up, that we can keep track by using this k. I will explain that. But let's say what is the spaces that we're going into, the extra part. So extra part is like when I pass this 3 to this 3, right? So this particular range is what I need to solve. This extra 1 means that this first element appears one more time, that is somewhere before it. Okay, so I deleted everything over here, right? So this 3 is now along with this 3, and I'm saying that this 3 will get deleted along with this 3. So there is this 3 over here, but there is some extra 3 that is hanging along with it, which will get deleted with this 3 itself. Okay, so that is what I'm saying is extra that is kept. Okay, make sense? Is this extra understood? So basically if I say that, okay, let's say there is some range, uh, some element 1 2 3 1 1. Okay, and I say that there is, let's call this range dp of 4 to 5 with extra 1. So this is nothing but like the range 4 to 5, that is this range 1 comma 1, and there is this extra 1. So this 1 means like count 1. Okay, so the first elements happens one more time before that. Okay, so it's like 1 1 1 right now, something like this. Okay, and this one and this one is going to get deleted together. Okay, it's now bounded together. Okay, now coming back to this particular like topic that when we are thinking about this 571, that when we were deleting, like when we are taking this 3 with this 3 and we are deleting everything else in between, and we are deleting 5 to 7 with one extra of 3 over here. So in that case, this is going to again call another DP that, okay, I need to delete, like this 3 gets merged with this 3. So in that case, this things get deleted. So 6 comma 6 comma 0 gets deleted, plus DP of I delete with 7 up to 7, and there was one hanging 3 with this 3, and now even this 3 gets deleted with this 3. So there are now 2 hanging 3s with this 3. Okay. Make sense? So this is that part where all of the 3s get deleted together is getting counted, right? Does this make sense that what we are trying to do, that we are trying to keep a track of how many like first element is hanging together, and we will match it with some next possible 3 where it will match, and everything in between must delete independently, and all of them that will carry from there, that is going to happen over here. Like this particular part is will handle that extra part. Okay, this K will handle. Is this state making sense now, what this state is keeping? We will code this, no worries. I understand that this is not like 100% trivial what we are doing right now, but yeah, our initial call will be dp of 0 comma n minus 1 comma 0, that we want to delete the range 0 to n minus 1 with 0 extras. Okay, that's going to be our initial call, and that is going to solve the whole problem, right? So we are basically enumerating on the choices for the first element's delete. Like, is it getting independently deleted, or it's going to get deleted with some next element, along with some next element. So whichever element that is, we are going to pass it to that element as an extra and delete everything in between. And then from there on, with that extra, solve the rest of the problem. Make sense? Okay. So I think like if the idea is more like making some sense, let's move into the coding part. I think that with that, it will make even more sense. Okay. Is that okay with everyone? If you have any doubt, you can ask, or else if you are okay with that, can I have a quick +1 so that we can move to the coding part of this? Okay. So I think coding this will make it much more clearer that what we are exactly trying to do over here. Okay. So I'm just going to quickly remove these things. N and arrays anyway is going to be there, so I'm keeping that. Okay. In this as well, we need to like there is a k square cost, so everything is going to be positive. So we can initialize it with -1. Okay, and my answer is going to be equal to. Let me delete these. Okay. So I will keep some sort of like recurrence to find the answer for 0 to n minus 1 with an extra 0. Okay. Now let's say we want to find find the answer for what is the answer for L2R with an extra K. Okay. Yeah, this is the thing that we have. And let's say integer dp is there to store it. So I will keep it up to some 101. Okay. So let's say we don't know the constraint yet. We will try to find out the best way. Okay. Now, first of all, we will try to write this case that if L is greater than R, then what is the answer? What is the maximum that you can like get as a profit if you have to delete an empty range? 0. It's not minus infinity. Like if you have like an empty range, you cannot get any profit, right? So it's 0. Okay. Like if I delete up to some point and then after that it's not possible to delete, it's going to be 0. Okay. Now let's say if dp of L comma R comma K is not equal to -1, So if it's equal to -1, then we will calculate and then we will return dp of L R K. Okay. Now we will keep an answer equal to let's say 0 initially. Okay. So now the first case would be like, let me draw it over here so that it makes sense. 3 4 4 4 3 2 3 3, something like this. Okay. So the first case can be this gets deleted alone, and then rest everything we have still as a problem. Okay. So that is nothing but, like, let's say initially there is a possibility that a single 1 into 1 happens. Okay. Sorry, there were k hanging, like along with this particular 3, there were k3s that were hanging with it, right? Like there are k3s that are going to get deleted with this 3. So in fact there are k plus 1 3s over here right now. So we will have to add a cost of k plus 1 multiplied by k plus 1, right? Because these are going to get deleted. Plus, what is the optimal way to delete L plus 1 to R with a 0 extra? Okay. Because 3 got deleted and there is no extra coming from the front. Make sense? Is this part clear to everyone, that just to delete this element there are k extras that are going to get deleted with this particular 3? So this is going to be my initial answer. Like this is one of the answers. Okay. Now we will try to loop over every possible element in the range L to R. Okay. And if, let's say, ARR of I is equal to ARR of L, like it's the same type. So I can, let's say the next, I am looping on every possible I. So let's say ARR of I is same as ARR of L. Okay. So then I can delete all these k plus 1 3s with this 3, right? So I have to delete things in between and I have to merge it with this one. So what I can have as a transition is answer equal to max of answer comma dp reference of, I will have to delete everything in between. So L plus 1 to I minus 1 I will have to delete, okay, with no additionals. Plus I will have to delete the recurrence of I to R with an extra of k plus 1. Make sense? And that's all. And done. So this 3, either this 3 is going to get deleted then and there, or it's going to get deleted with some next 3, right? That's what we are doing. We're iterating on every possible next 3 that is there. Okay. And we are going to merge it with that 3. And this is going to be that merge, that all these now k plus 1 is going to hang with this 3. 3 3 3 is there. A lot of 3s is there. It's going to get deleted with this 3 only. And then there are choices that this 3 can then again get deleted alone, or it can merge with the next element, or all these k can directly get merged with this one, and this all things need to get deleted. Okay. That's all of the iteration that we are doing. Is this now making sense? That's the whole code, in fact. The code looks quite small. There should be some condition on k on recurrence. The condition is, so it's never going to be more than like the number of maximum frequency, right? It can never be more than that. Okay. Can you explain how this state counts over all possible combination of states? Okay. That's what we are saying, right? That when we are like at this 3, and then there are 4s, and then there are 3s. So what is the, like there are k extra 3s that are there with this 3. Okay. So what are the possibilities for this 3? That this is going to get deleted alone, like with alone, and this part is handled separately in the delete, like subarray delete, or everything in between gets deleted first. So this 3 is going to get merged with this 3, right? That is handled by this particular part, right? Or else all of these things get deleted and this 3 is going to get merged with this 3. Okay, that's one possibility. There is another possibility that this 3 might get merged with this, and then this 3 gets merged with this, but that is also handled in the first case, right? When we had k over here, so we went to this plus this one as k plus 1, and then for this 3 we will get a choice that, okay, it can merge with this tree. So you can reach to this particular state that I have k plus 2 trees at this particular state. So it's possible to reach this state. Okay. So that's why we will only consider the immediate mergings, that okay, this tree is going to get merged with this particular box and everything in between is going to get deleted, right? Make sense? That's how, like, for the, like, across all the combinations, the first element has to get deleted, right? So we are counting on all possible ways to delete the first element. That's it. And it has to get deleted, right? Across all combinations, there has to be some way in which it's deleted. That's what we are counting. Is this making sense? Now, so the big question for this would be, let me see if your concept of DP is clear or not. Think about this and tell me what is the complexity for this problem and why, more or less. That's the idea. What's the complexity of this particular state problem? Think about it. Like, this is the code. Okay, what is the complexity of this code? N cube into k. K can be up to n only. Like, what is k? I'm not getting that. Like, k is not an input, right? So you need to tell me the constraints in, yeah, okay, n to the power 4. So you need to tell me in terms of constraint, like input is only n, there is no other input. K is not an input. We are creating a state key. Okay. So I will say n to the power 4. Okay. N cube. Okay. The actual power demand is very small, but anyway. So it turns out its complexity is something. Let's look into how we get to that. Okay. So think about this particular array. Let's say let's talk about those positions where we have one. Okay, let's say there's one over here and there are some other elements, then there is some one, there is other elements, and so on, right? Make sense? Now for this particular one, if you think about it, like, let's say this particular one, okay, this particular one over here, okay, let's say there are x1 number of ones. Okay, for this one over here, how many different r cross k combinations are there? So for this one over here, r can, like, this particular l, this is the l fixed. Okay, and then for this l, r can be any value, like over any one of these. Okay, so r can take, like, l to n. Okay, so that there is like order n number of values for r. Okay, k can take order xi number of different values, right? Okay, and for only if you think about ones, like the positions where one are occurring, how many different l's can it take? Like, how many different l's will have one in it? L can also take order xi, right? Make sense? So let's forget about l's. Even if l is all like n's, okay, l are all n. Okay, k can take only xi different values, right? From 0 to xi. That is the number of ones in the whole array, right? X1, I mean to say. Okay. So the number of different state that will have the first element as 1, okay, is going to be equal to n into x1. Okay, these are the different states. That's the only number of states that you can go to, right? So the number of different states which have the first element as 2 is going to be equal to n into x2. Okay, so on. Make sense? And the total number of states that there can be up to summation of this only, right? This is it. Okay, it can be only up to summation of this. Okay, so this summation you can write as n square into summation of xi, which is going to be equal to n, right? This xi summation is n. So this whole complexity is actually nothing but order n cube. Okay, so even though it looks like it's n to the power 4, because for every state, for every particular state we are doing an order n computation. Okay, the k can not be like up to n for every state, right? So this particular loop, this particular number of different ki values that you can take, right? The number of times the transitions are happening, okay, that is never equal to like uh, order n. In fact, like this is always order xi. So in total, this is going to get to a summation of order xi. Make sense? Okay. So this is the total number of different states that we can reach into. Now there is one possible like small thing that you need to notice in this particular implementation, that we are doing something very inefficiently in this. Can somebody quickly tell me what that is? Like something that we are doing inefficiently, and something like we can improve on in complexity in terms of overhead. So why are we looping over everything to get the next occurrence, right? Like why are you even doing this? This we can, like, for every element we can separate, like keep a positions, right, where all they are occurring, and then for that particular L we can go ahead and find out what are the next occurrences. We don't need to loop order n over here. We can do an order xi if we want to, right? And that will reduce like the summation to this particular summation, and it is going to be order n cube into. Okay, is this making sense what we are trying to say over here? Is this clear to everyone? Can I have a +1 if this is clear? So time complexity part you can leave, but I hope like this particular idea of deleting a subarray, how do we handle deletes of subarray? That is a very important idea, and it comes up in a lot of like good questions. And once you know this particular state, you can think about that anytime, right? So you just need to find out what is the number of like, how do you keep track of that number? That's the main thing, right? That how do you move into the next state? So for the first element, we try to count on different possibilities that we can do for that. Yeah. And that you can do using just like iterating on every next element. Like where is that next element up to which you will delete and merge this one with that one. Okay. That's what we are doing. Okay. So I think that's all for today. So these are, so today we just took up a lot of different application ideas of LRDP, okay, or interval DP that we talked about. So we'll stop up to this one.